This is the Amp Hour Podcast. Released February 24th, 2020. Episode 481. Sponsored by Keysight. An interview with Paul Thompson.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
G'day, I'm Paul Thompson from Pacton Technologies in Brisbane.
Hey, Paul, thanks for joining us.
You're welcome.
This is a rather a lucky event, really. I found one of your products in the dumpster, a really old version of your product.
Yes, I eventually worked out, I think I worked out how it got there. We'd sent it away for testing, for EMC testing many years ago, and sometimes you just don't get those things back.
Really? Is that I think we've always gotten ours back, but really they just keep it for what purpose?
Yeah, it depends how the testing goes. For example, I know of another case where we sent some items off for electrical safety testing, and then there was an earthquake in New Zealand. We didn't get those back.
Oh, okay, right. That tends to disrupt things a bit.
Yeah, disruption, change of personnel, that sort of thing.
Tell us about Pacton Technologies and what you guys do and what you do there.
So Pacton's, we're an electronics design and manufacturer. We began in 1995 on the back of an invention, and that invention was a electric fence fault finder. I was the first person to put to market an electric fence fault finder that actually was useful in that it said which way the fault was. It gave the direction to the fault, and it did that by analysing the current flow in the electric fence live wire. So having invented something, like a lot of inventors, I thought, well, I'll just sell the invention. So I found
Right.
found the largest company in the area of electric fencing and tried to sell the invention, but that didn't go very well. So I ended up starting the company.
They just weren't interested, or they stole your idea, or
The latter. They were very interested.
So you started your own company.
Yes. So in order to exploit the idea, we started Pacton. Really, 12 months prior to starting it, I was happily working for a company in the area of electronics weighing, making digital scales. And we had so much interest in this invention that we started, basically started as a second job. And then when the month that the income from the second job overtook my main job, I thought, well, we probably should make this a serious company.
That's how all good companies start. They start in the garage as a part-time enterprise.
Absolutely.
And then once it hits that tipping point, yep, see ya. Not working for the man anymore. That's terrific. So Pacton, so that was about mid-90s, was it?
It was 95, yes.
Right. And nobody else had done an electric fence fault monitor before. They just did the controller which just powers the fence. Is that right?
There was the fault finding tool. The best fault finding tool on the market at the time was just a voltmeter. So farmers had in their hand a device that told them what the voltage was on the fence, and they had all sorts of tricks to isolate faults. Basically, divide and conquer. Open a switch that does the voltage on the fence jump up. Okay, then I must have isolated the area of the fence with the fault. Not very intelligent design.
So would they have like these switches installed periodically along the fence, and
Correct.
they can just go and lift them? Okay, right.
Cutout switches.
Got it.
So that was the technique, and basically, looking for a drop in voltage was people who were a little bit more savvy would know that as they approached the fault, the voltage would drop. No, there was all sorts of other crazy ideas. AM radios tuned off station to listen to the static of the basically looking for an arc on the electric fence, which might signify that there was a short.
And you'd hear that arc every couple of seconds or something?
Every second. So electric fence energizers, predominant type of electric fence energizer now for many, many years has been a capacitive discharge circuit that pulses about once a second. And all of our safety standards and all of our design has gone into that type of circuit now for the last 20 years or so. Prior to that, there were some electric fence energizers, in fact a lot in the US, that were a simple step-up transformer. Hence the common knowledge, if you like, which is now wrong, that electric fences are high voltage, low current. They used to be. It used to be a simple AC step-up transformer, and they were current limited, and therefore they were safe because they didn't deliver enough current to cause electrocution. But they were dreadful at their job. It didn't take much load on the fence to drag the voltage down. So the capacitive discharge circuit was kind of the third. There was an intermediate where people were using a Kettering ignition circuit, which is essentially the same as in the old motor car circuit, where you've got points that close on the primary of a transformer. Current builds up, you open the points, and you get flyback, and hence a spark.
Right.
But again, the turns ratios on those transformers was such that the output impedance was quite high. So a capacitive discharge circuit's a low impedance output. It can deliver high voltage and high current, and that's a much better device to put on an electric fence.
But more dangerous.
It can be, hence the rules. So, like most engineers, we live in our standards. So there's a base standard for electric appliances under the IEC, which is 60335.1. And then there's our particular derivation for electric fence energizers, which is .2.76. And that's quite a weighty document. And there's a lot of really good science behind, why if we adhere to that document, our products are safe. And that science, that was had been done before I left university, which was in 1983. So it was well established.
Are there different standards for, like, ones for animals, ones for humans, ones for, like, keeping people inside prisons? Because there's lethal ones as well, isn't there? There's like a dual mode one where it'll zap you first, and then if you keep going, it'll kill you. Is that right? But that's not something you guys do, though, right? You guys are more into the cattle control kind of field. Is that right?
Well, we started in the cattle area, and then we found the need for security electric fence energizers. And these days, about 75% of our business is the security electric fencing. It's a huge industry, and you're quite right in that there are these well-defined sectors. So there's agricultural electric fencing sector, which is all about keeping animals in. There's security, which is all about keeping the bad guys either out of your house or out of your military establishment, or there's prisons where it's about keeping the bad guys in. And you're right, there is lethal electric fencing, but I think you'd be hard-pressed to find any these days. I think South Africa and the US were the last to use lethal electric fencing, and South Africa turned all of theirs off at the end of apartheid. And I don't know of any in the US anymore. So, and you're right, we never touch the lethal electric fencing. We operate in the very safe, mandatedly safe area of electric fencing for humans and security. And it's only talking about the safety standards. The standards for agricultural and security only just diverged very recently. Until then, they were the same standard, dictating the same limits for the pulses.
So what made them split it out?
I'm on an advisory group to the IEC committee that drafts the standards, and essentially it was the fact that the agric people didn't understand what we were doing in security and why we had this need for a separate standard, doing things differently. And rather than it become an argument, we started to diverge parts of the standard to cope with these, two different areas. Just one obvious way that the energizers differ is that in agricultural electric fencing, you rarely use more than one electric fence energizer on a farm. Some farmers might use two, but they'll be on different parts of the farm. They'll be on different fences. Whereas security electric fences are zoned, and each zone is powered by a different energizer. And for safety's sake, those energizers need to be synchronized. And that's just one of the small ways that security energizers are a lot more complicated than agricultural electric fence energizers.
Do the agricultural ones, do they have more joules behind them? For example, like does a big cow require a greater zap than a human? I would presume so. Is that right?
Yes. So there's been something of a competition around the world for who can say that they've got the biggest electric fence energizer.
Right.
And that's been going for quite some time. So
who's currently winning that? You guys?
Who's the winner? We've never been in that race, Dave.
Okay.
We didn't really see the point, and
got it.
Engineers will appreciate that as you near the edge of anything, trying to get the biggest, the fastest, the amount of engineering and the amount of cost goes up exponentially.
It does. Yep. Very diminishing returns, so to speak.
That's the word. So, yes.
Right. So you guys, so you're in Australia. You manufacture all your devices here. Is that right?
We try to keep a lot of our manufacturing in Australia, but we have some customers in very price-sensitive markets.
Of course. Yeah.
About 80% or so of our turnover is actually exported. And some of those customers are in, for example, South America. So we sell to, we have a customer in Chile, and it's a price-sensitive market. There are a lot of locally made products in places like Peru.
Interesting.
In order to compete on price, we do have to have some of our stuff made in China. It's just a fact of life. The Chinese are very good at making electronics. A lot of our components come from China.
What about because there's a few custom transformers, for example. Can we talk about transformer design? That's a good segue into because you designed one of the first. You designed the magnetics in your original one. Do you still design your own custom transformers?
To a certain extent, I work closely with transformer specialists on that.
Right.
It's not my forte. I have been forced to learn a lot more about it.
You're right.
I guess if you were to say what my specialization is, it's microcontrollers. Before Pacton, I was employed, writing assembly code in a 6805 Motorola microprocessors for weighing equipment. 6809s, cut my teeth with HC11s, things like that. And a lot of assembly language, a lot of squeezing bytes into little micros for low cost mass production. So magnetics, pulse transformers, right. Interesting things, because we're trying to get a lot of power through the transformer very quickly. Overall average power, if you like, if you look at what power, you think about it in terms of the laws of thermodynamics, draw a box around it, what power is going in, what power is going out. For the typical energizer, it's only about 10 watts. But the instantaneous power output out of the transformers is enormous, because we're talking about almost 10 kilovolts, reasonable numbers of amps. So it's instantaneous power-wise in the tens of kilowatts. So that transformer's an interesting beast. It has to handle very high current through the primary. The inductance is important because we're trying to produce a very short, sharp pulse. So we've got to keep the primary inductance low, hence the turns ratio on the primary is low. We've got to have a reasonable step up, but not too high. We do some of the step up in the primary, so we charge our primary capacitors to a reasonably high voltage, approaching 1,000 volts on the primary. So our step-up ratio of our transformer is typically between 10 to 1 and 20 to 1, depending on the energizer we're producing. And the core, the other thing, of course, is we want the core to not saturate in a hard and sharp way. We want it to be a soft saturating core. So we're using a particular type of sintered iron core that gives us a softer saturation. So not all of our power is lost in I squared R losses once the core saturates.
So for those who don't know, it's basically a two-step process, right? There's a first step-up transformer, which is switched via a MOSFET, and that's intelligently controlled via the micro, and then that charges the capacitor bank on the secondary at, as you said, up to 1,600 to 1,000 volts maybe.
Yep.
And then after that, you've got the output transformer, which is then driven via a high voltage SCR, which then dumps the energy to the output. Is that correct?
Absolutely, yeah. So the DC-DC's PWM, we manage that from the micro. We've been using micros with PWM peripherals built in for a long time, quite successfully, and that reduces the part count, which is nice. The DC-DC, of course, it's not a classic DC-DC in that we've got a variable load, so to speak. When you think about
of course,
a DC-DC operating into a capacitor that's just been completely flattened, it's as if it's operating into a short circuit. And at the other end, it's topping up a capacitor that's almost at 900 odd volts. So it's almost like it's operating into an open circuit. So the DC-DC transformer design is also a challenge, but not as much so as the pulse output transformer. And capacitive discharge. So high voltage on the caps, and then you switch on the SCR. And of course, those things switch on, but they don't switch off. They'll dump the whole capacitor straight into the transformer. And
it will dump every joule into the fence. Is that the idea? Does it completely discharge? Or
Yep, that's what you're hoping. And we manage the primary because, of course, we're using very low ESR capacitors. A pulse capacitor is essentially a metal film capacitor that's had its terminations beefed up, so it doesn't shock itself apart when you do this to it.
Yep. In the teardown I did, you were using Australian-made Plessey capacitors. Do you know when they stopped making those here?
Oh, look, it would have been in the late 90s, I believe. So we were still using Ferguson transformers.
Yeah, Ferguson's, yep. All of the Australians will know Ferguson transformers, yeah.
Yes. And then there was another transformer manufacturer in Sydney for a while, and I think it was ATA maybe, and they were taken over by a German company that was only interested in their fluorescent ballast transformer design. So they ceased making transformers for us. And then we went to New Zealand and found a little transformer specialist in New Zealand. And we were really fortunate that the guy over there was an absolute legend, designer Bob Smith. One of these old grey hair guys that knew everything from first principles.
That was Marquee Magnetics.
That's correct.
So he was an old transformer greybeard.
Absolutely. Yep. The things he could tell you. I long after he'd retired, I sought him out because I had a peculiar problem. Some of our output transformers were burning a short circuit through an interlayer winding, and it was happening in a particular part of the transformer. And I thought, this can't be coincidence. There's something going on here. So I sought Bob out in his retirement and showed him some teardowns. And he said, "Oh yeah, I can see what's going on here. You've got a standing wave."
A standing wave in the transformer, and then it would arc over at a certain point, would it?
Certain point. So yeah, the fence, a tuned circuit on a stub of fence, shooting a high frequency back to the output of the transformer, and then just belting a transformer in a particular point of the output where that wave reached a maxima. And I'm glossing over the serious complexity of that.
Of course.
Really, these old guys who could sit down and sketch out the equations and do it all from first principles absolutely had my...
yeah, totally. Well, one other thing in the teardown of the old prototype unit, I noticed, I haven't torn down your new one you sent me, by the way. Thanks for that. I haven't torn it down yet, but I'll eventually get around to that. Was that because you sense the output voltage on the terminals and you feed that back via an optocoupler, and the optocoupler was literally like a LED and a photo transistor, I presume, inside a long heat shrink, a custom, just heat shrink tube. Can you tell us what story? I presumed in the video that you couldn't get an off-the-shelf opto that was good enough, so you just rolled your own. Is that?
Well, it's partially true. We did start with an off-the-shelf opto, but our particular safety standard that I mentioned before dictates that we need to have an isolation barrier between primary and secondary with a creepage distance of not less than 25 millimeters.
Oh, 25.
Try finding an opto with lead
Yeah.
spacing at 25 millimeters.
25 millimeters. Ooh.
Mm.
What is the biggest one out of interest? Would you know offhand? What is the biggest clearance one?
They are available up to about rated at normal voltage of 4 kV, and the lead spacing is about 13 to 14 millimeter, I believe, on those packages. But when we looked at that package, we realised that essentially all it was the photodiode and LED and photodiode or phototransistor in a package, and we thought, well, we can do that. So,
Yep.
but we've made a much prettier one since then. We've moulded our own plastic.
But it's still a custom made job.
It is still a matched infrared LED phototransistor, and we're using it in a linear part of the curve, so at about 10 milliamps.
Mhm.
It's reasonably linear, and I found that by mistake. I actually did a 2 opto. I did an opto linearization using op amps with an opto in either direction.
Right, because that's important because you actually sense the actual voltage, right? So it's got to be used. Well, it doesn't have to be linear. You could compensate in software, but
Correct.
it's nicer if it's linear.
Well, yeah, I did this, complicated circuit. It's probably one that I found in one of the old national linear data books to compensate a non-linear device with op amps. And then I had the crow out and found that the linearization was doing nothing. I'd actually hit the devices in the linear part of their curve. Happy accident.
Crow, just for our American audience, a crow is an oscilloscope here in Australia. Still is. Thank you very much. Just want to clarify. Yeah, cathode ray oscilloscope, crow. Fantastic. So you dump all of the energy from the capacitors into the output once per second, and then how long does it take to recharge? Does it take almost the full second to recharge them?
Yeah, well, it turns out the most efficient way to run your DC is to give it the maximum amount of time to do its job.
Yeah, of course.
And we on our bigger units, we're also doing intermediate feedback. So we're looking at the rate of rise of the voltage on the capacitor. We're making sure that the caps aren't shorted, and we're not going to cause a fire if we try and charge a shorted capacitor. The capacitors are under a lot of stress. The capacitors and the output transformers are the reason why electric fence energizers don't last forever.
Okay, right. Of course, yeah, because you're just dumping massive amounts of energy every time. So there's going to be wear and tear on those, not only the caps, but your output transformer as well. And
Correct.
Even your SCR might snot itself eventually, I would presume.
Yeah, well.
Or are they fairly rugged?
They're a very rugged device, but you've got to turn them on hard. If you underdo the gate current on an SCR and it's presented with it's trying to switch a high voltage capacitor and it's going to ramp up its cascade current very quickly. If you underdo the gate current, you'll find that there'll be regional hotspots in the SCR internally, and they'll burn out. So yeah, good gating circuit. They're also the first in line if a lightning strike comes in from the fence. It'll go through the transformer and zap the SCR. So we do. You correctly pointed out in that the one you tore down, you found some spark gaps on the circuit board.
Yep.
So that's the first line of defence for lightning coming in, because essentially where farmers are hanging a big aerial in the field on an electric fence saying come and zap me.
I know, zap me. Yeah, that's right. Is that common? Like, how often would they get zapped? Are they like more like? Does it happen like every lightning storm or?
Every lightning season, we get an influx of people presenting us with dead energizers and or wanting to buy new ones. And sometimes it's very obvious. I could send you a picture that shows that there was a lightning strike and the energizer was on the wall. And after the lightning strike, bits of the energizer were all across the floor.
Oh, yes, please send the photo. Everyone loves destruction.
It was black and charred.
Yeah.
The good thing was, my comment as an engineer involved in the safety standard, my comment back to them was, well, I'm really glad to see that everything's self-extinguished.
Yeah. Oh, so how big do you spark? Do you use MOVs, or do you prefer MOVs or spark gaps, or what? Which is better, and how big do they have to be, or is you can't get them big enough for? they're going to eventually.
Lightning's a whole area of expertise, and I was lucky enough to do my final thesis at UQ, University of Queensland here in Brisbane, on lightning.
Mm-hmm. Oh, wow.
The trick is to stop it before it gets into your box. So we encourage farmers to put a lightning diverter out on their fence. If they can divert the energy before it gets to our box, that's great. And then we put, secondary and tertiary on our board, so there's a spark gap near the terminals in case it's coming in. Then there's MOVs. Then there's our transformer. And then on the primary, we're looking to capture reverse pulses, because, of course, you can't dictate what polarity the lightning strike's going to come in on the wire. For those of you who know a little bit about lightning, the majority of lightning pulses are at a particular polarity, and then every now and again there's one on the opposite, and that's usually at the worst.
How does the polar? I didn't know nothing about lightning. I think it's fascinating because ones can go from the ground upwards or from the sky down, can't they? Does that determine the polarity? How does that?
No, it's the shape of the thundercloud. So typically,
there's the shape.
The thundercloud is a dipole, so a big dipole is built up in a thundercloud, the underside of the thundercloud. And forgive me, but I've forgotten the actual polarity.
That's all right. It's about 30 years, right? 40.
It is a while ago. I think the bottom of the cloud is negative, and that then induces charge on the land underneath it. And then you get the leader stroke, which actually comes up from the ground. And no one ever sees that. That's the start of the leader stroke is also known as St. Elmo's fire. And people do see that. So a corona builds up on a sharp object on the ground. A leader stroke or a stream of ions goes up towards the cloud. And that opens up a charged path. And then the lightning strike comes down from the bottom of the cloud. But as a thunderstorm passes, sometimes the cloud can be skewed by winds, and that reveals the top charged section of the cloud above ground, and that's the great thumping big strike at the end of the storm that can do a lot of damage.
That's fascinating. How do these lightning arresters work on these fences? Are they just giant spark gaps in their own right?
The simplest is a spark gap. So the simplest lightning diverter of all is simply a spark gap. So you tune the spark gap so that it won't arc over with our normal electric fence voltages. And then lightning strikes the fence and races down the fence wire, finds the spark gap as the easiest path to ground. And that then limits the voltage surge that can come along the rest of the wire and hit your energizer. But we make a more complex one, which is a multi-stage device. We pot up a three-stage lightning arrestor in epoxy so that we can shrink it down using the epoxy as the insulation. And that one's got a spark gap, an inductor, metal oxide varistors. And in the center, we put an LC circuit, and then we go out the other side with the mirror image. We joke that that's because we can't trust a farmer to put it around the right way on a fence, which is a little bit demeaning to farmers. But in reality, it was the easiest way of making it. We made it as a T filter, and on either end there's a lightning arrestor. And the other reason for that is that when a farmer puts it out on the fence, it's actually possible for the surge to come in either direction to the lightning arrestor. So we made it symmetric.
A couple weeks ago, we heard from Daniel from Keysight talking about ESD and test equipment. I was pretty surprised to find out some of the things that could damage equipment, but there's actually more.
There's other things you can do to keep your stuff safe. So one of the things that people miss is this inductive charging. So if you have materials, often it's packing materials. So you get a box from somewhere, it's either your boards or someone shipped you the equipment or even rolled it down the hallway on a cart. That's all building up charge. So one of the worst culprits is that pink packaging material that you see all the time. If you have those materials around, keep them like a foot or more away from your exposed assemblies. So that just keeps it from inductively charging. So you have this charged up material and it's going to inductively charge things around it. So your boards are included in that. If you're transporting them around, put your boards in static bags, kind of that standard stuff, and then make sure you're, grounded and your mat's grounded when you're actually handling your boards.
I had never heard that about pink foam before, but I thought that was super interesting. And it left me wondering, what else could we be doing to keep ourselves safe?
When you go to look into ESD best practices, you see a lot of here's how to protect your boards and here's how to protect your manufacturing line. But what you don't see is here's how to protect your equipment. Because what happens is your board gets charged up, and maybe that's okay. Often that's not going to be a problem. But as soon as you cable it up and go to connect it into your input, if that center conductor of your cable goes into the center conductor of your input, then all the charge on your board is going right into your equipment. And that's where we're seeing the damage.
You may remember that all of this information is available as app notes and as videos. And it's also being shared as part of Keysight Wave, which is a contest that's coming up from Keysight starting March 2nd of 2020. You can enter and win a wide range of test equipment from Keysight.
Make sure I say this right. Every day we're giving away 5 200 megahertz 1000X series oscilloscopes, 4-channel. We're also giving away 5 of the nice handheld DMMs, 1282. And those are great. I have one at home, one on my desk. I use them all the time. And then we also have a sort of grand prize winner each day, and they can choose their pick of like a scope or a DMM or a system, like a power supply system. There's also some RF stuff in there. So there's a signal source, if I recall. And then on Fridays, we have like a big draw. So you could pull one of your choices is a Field Fox, which is like a combo signal analyzer, VNA. And there's also, I think, a USB vector network analyzer, like the P5000. It's really cool. It's super small, and it's great.
Keysight is offering Amp Hour listeners 2 entries for every time they put 1 entry in. You can enter right now, and drawings start on March 2nd of 2020. You'll also get access to app notes and videos and a bunch of other things, not to mention a chance to win all of those great prizes that Daniel just listed. So go check that out. It's bit.ly/amphourwave. That's bit.ly/amphourwave. The A, the H, and the W are all capitalized. And now, back to the show.
Back to the transformer design. In one of your emails to me, you mentioned that the design of the transformer, the design was all about doing a term I had never heard before, which is a soliton pulse shape. And I had to look that up, and it looks very much like a bell curve. What is a soliton pulse shape, and why is that is that an ideal electric fence pulse shape, or?
So a soliton, I guess if you would define a soliton wave, it's a solitary wave. Solitons in nature, think of tsunami. So a tsunami is a wave that travels across the surface of the ocean for long distances and retains a lot of energy as it travels. And it's almost a singular wave. Another way of defining a soliton is it's the perfect wave shape to travel undiminished in a particular transmission line or on a particular transmission line. Solitons are used in fiber optics. I guess it's remained a bit of a curiosity to most people in the world, but it's the perfect wave shape for a pulse of electricity on an electric fence. All things being equal, we can't dictate how a farmer builds their electric fence. They could use a single wire, 2 wires, 3 wires. That changes the characteristics of the electric fence as a transmission line. And electric fences start to attain transmission line characteristics when their length exceeds around 5 kilometres. And again, I've taken an oscilloscope out to electric fences and checked this, and you really start to get a deterministic input impedance. So even though you might put a short circuit on the fence at a point beyond, say, 6-7 kilometres, you actually don't see any change to the input impedance, the looking into the electric fence, because it's become a transmission line. It's got a fixed impedance.
Fascinating. And is that what's that based on? What length is that 5 kilometers based on? Is that based on the timing of the pulse, or
the wavelength essentially? So so if you think about if you start to think about it in terms of frequencies and frequency response, we're jamming a short sharp pulse in there. It's got the majority of its power at a certain frequency and above, multiples thereof. Uh-huh. And that is high enough for that single wire strung above ground to act as a transmission line at around those distances I mentioned, 5 kilometres and beyond.
Right. What's 5 kilometres in frequency?
Oh goodness!
I could get my calculator out, but I can't see it. Anyway, it's a long wavelength. Anyway, let's put it that way.
Yeah, look, it's tens to hundreds of kilohertz. Yeah,
it's incredible. Right, so that sort of bell curve like is how I'm going to explain it, because unless you've you can see an image. It's almost identical to a bell curve, really, bell shape.
When the perfect soliton for an electric fence, and a way to analyze or find the soliton wave shape is to jam an impulse, a perfect impulse, into the transmission line and see what got to the end.
Yeah, of course. So you just put a short, sharp pulse in and then check it out. Yep, that's a common way to
see what gets to the end, because everything else is going to be filtered out. Another way of thinking about electric fence design is that it's pointless throwing a pulse shape into the start of the fence that doesn't get to the end. So figure out the pulse shape that's getting to the end. That's the pulse that's traveling. That's what you really want to generate. Any energy that you're putting into the fence that's outside of that curve is just wasted. It's going to be reflected back or soaked up by capacitive effects.
And that's why you want to shoot for that perfect soliton shape, is because there will be, in theory, zero losses, zero energy lost on that transmission line, in theory.
In theory. And of course, going back to what I said before, we can't dictate how they build their fence. And also, the electric fence is a very lossy transmission line. For a start, they're using steel wire, which has an impedance of around 40 ohms per kilometre.
I was going to ask about that, yeah.
and then there's grass and cobwebs and dusty insulators. And but of course, the object is to try and get the highest voltage possible on at the end of the fence. And as far as the quality of an electric fence is concerned, the measure of quality is, what's the zap like? In terms of a farmer, he says, is it going to zap my cow and keep it in the paddock? And we translate that to how good's the voltage at the end of the fence. So let's make an energizer that does the best at getting the best voltage to the end of the fence.
Got it. So do you have a tester that can go on the end of the fence at that particular wavelength and check that? Because one of you said before, one of your first product was literally a electric fence monitor, like fault monitor kind of thing, and you still make those these days. So an electric fence is capacitively, it's basically a capacitive load.
Yep.
Right. So can you tell us about how can you determine where? You said you can determine a fault within 1 in 1,000 or something. So if it's 1 kilometer long, you can get to a meter. Tell us how you can do that.
I mentioned before that a lot of our business these days is in security, and security electric fencing. There's kind of a crossover between agriculture and security, and that's the what they call game parks in South Africa. Most of you are probably aware of a place called Kruger National Park in South Africa, where they have rhino. They have the big four. They have rhinos, lions, elephants. It's a beautiful place to be. I've been fortunate enough that my job has taken me there, and I've literally put, through attenuators, put oscilloscopes on the fence at Kruger National Park and had a look at the waveforms.
Fantastic.
But those fences are under a lot of pressure from both directions. So, things like rhinos would like to get out through the fence, especially when there's another rhino on the other side and they want to have a fight. Male rhinos tend to be territorial. And then there's poachers trying to get in. And this is the bit that, I guess I'm most passionate about, is that our technology is being used to protect rhinos in South Africa against poaching. So we determined that these security electric fences were already being wired in loops, which is something you can't convince an Australian farmer to wire his fence in a big long loop, because that would
Why
be
is that?
Well, it's just not convenient for them. It's convenient for them to make a tree shape or a grid or a mesh, but when you're talking to installers at places like Kruger, they're listening. They're saying, "How can I make the best fence?" And we say, "Well, we need to know that it's working, so you need to wire it out and back in a loop, so we can bring the voltage back to the energizer / monitor to be monitoring that every pulse that we send out is getting all the way out there and back again." And we can do that on a straight line fence by going, out on some wires, turn around at a certain point and come back again on some other wires on the fence. And these game park fences in South Africa.
So you got to have a return wire physically installed
Correct.
on the fence. Okay.
Feed and return. And for a security application, that return can be a single live wire. So you might have a security electric fence. Often looks like a massive number of wires. You can have upwards of 20 live wires on a security electric fence that's keeping people out. On these crossover fences for game parks, they typically have 6 to maybe 10 live wires. They're pretty tall fences. They're 6-foot fences, and they'll have live wires on either side and sometimes also on the top, because elephants will provide downward pressure on the fence to try and break a fence.
Oh.
There's a number of live wires that you can then decide, well, okay, I'm going to use 4 out, 3 back. So there's a dividing point on the fence that's the end of one zone and the start of the next. Once we started looking at the waveforms, we realized that if we analyze the current, and particularly if we analyze the real current, so now we're getting into real and reactive currents.
Exactly. Yeah, you have to, because it's a capacitive load.
The reactive currents are circulating. They're there all the time, and they're large, and they've got nothing to do with faults on the fence. And so reactive currents are because of the capacitance and to a lesser extent the inductance of these long wires. And we said, well, okay, if we can look at the real current and we can tell where that current is going, we can find a fault, especially if we look at a big loop of fence and we can ask the installer to make that loop as symmetric as possible. So now we're talking more about having an even number of live wires, say 3 going out, 3 going back, one big loop of live wire. And we actually we split our pulse at the start and we feed in 2 directions. And we analyze the signal going in those 2 directions. And by simple, differential, by saying, okay, if there's no fault on the fence, then the signals, in particular now the real currents, should be equal. There should be a point at exactly 50% along this fence where the current's null. And if there's a fault, that's going to upset that null, and we're going to be able to work out where that fault is. The first time I sketched this out, it was a page of math. It's not rocket science, but it is some math, and we've now got that into a device, and its accuracy, it's actually measured accuracy is 1 part in 10,000. That's the accuracy of the math.
Nice.
But in reality on a fence, it's about 1 part in 1,000. And if we're talking about 5 to 10 kilometres of fence, that's still only a relatively short position on the fence, which means that we can put that up on a mimic screen in a control centre for a park, and they get an alarm, and then it says, okay, on the map, it's this point on the fence, sector 19, on this fence that's just west of such and such gateway, and they send the guys out with the AK-47s, which is when you realise it's serious.
Wow. So you can detect opens, shorts, heavy loads, maybe? What different?
All 3. By different measurement techniques, we can tell if the fence is completely healthy. That's the easiest thing. We can determine that there's a hard fault. In other words, there's current bleeding out somewhere. We can determine an open circuit because we lose continuity, and we can determine a poor fence, in other words, a maintenance condition. You'll appreciate a lot of fences in parks like this. In the tropics, for example, there's all sorts of succulent weeds that want to grow over your fence.
You're right.
And some of those will actually arc. So you need to...
oh, yeah, of course. Yeah.
Yep.
So do you do all of this detection using the actual pulse itself, or do you switch out the pulse and put in other detection circuitry periodically?
Now we're getting into some of our secrets, Dave.
I knew it. I could sense it. My spidey sense when that was my design spidey sense saying, yeah, I'd probably do something like that.
Probably superimpose another signal to do another job for you.
I'm sure you've got patents on this and people can read all about it, so it's not secret. You just can't copy it, right?
Well, the patents give you a degree of time of secrecy. So patent will do things for you. You drop a patent in when you think you've got a good idea. In the Australian system, that means we've got 12 months to then put a full provisional in.
Yes.
To a certain extent, a patent is largely invisible until it starts to be challenged or starts to get to the later stages. So you won't be able to search online for that particular patent. But once it goes through, after about 2 years, basically, it starts to be revealed. Yeah, so for a while, we've got the best of both worlds. We're keeping it secret and we're patenting it.
Let's just say that you don't just use the pulse. There
Correct.
are other things at play. Okay, got it. So what can you do if you've just got a typical farm and all they've got is just one fence that you don't have a return loop? You've just got the one wire going out. Can you do anything to detect? Can you do like a TDR, time of flight thing, get the reflection back to determine faults?
You can. I've still got a box at work from when one of my engineers started down that track of TDR, and I pulled the plug on that because it started to get too complicated.
It could quickly, I'm sure, yeah.
For those that know TDR, think of a hairy caterpillar.
Hairy caterpillar. Okay, this is a new analogy.
That was what the signals were looking like. So we weren't getting a clean echo. If with TDR you're looking for a clean echo at a particular time.
Yes, of course.
And ours was more like a hairy caterpillar. We were getting echoes and glitches everywhere.
Is that because the nature of the, there's all the poles and there might be a little bit of, loads everywhere all the way along? Is that
the farmers tie wires together, and each one of those is a reflection.
Yeah, of course. Oh, of course. Yep.
So
Got it.
Hence I pulled the plug on that.
Uh-huh.
There's easier ways for doing it. One of the ways is to put a Sentinel type device out on the fence to report that the voltage has got to a particular point.
Oh, okay. So that's a wireless thing, is it? Or
Yep. So we've got a what we call an IP monitor, which goes out on the fence. But for the 99.9% of farmers out there, they'll rely on the reading from the electric fence energizer. So we've got IP electric fence energizers as well, and they can look on their phone. And if they see a slight drop in the voltage at the energizer, that gives them a clue that perhaps there's a fault on the fence, and then they can go and test the fence with their voltmeter. For more serious farmers, we actually put the security type gear to work for them. So we build electric fence stations, which are field cabinets, solar powered, report to the cloud, then to their phone. And those fence stations are looking at the current. Sometimes, as I said before, it's hard to get Australian farmers to put a return wire in. But if they do put the return wire in, because they don't want to waste a wire on their fence. Australian farmers are typically only got 4 or 5 wires. They want every one of those to be a wire that zaps the cattle, not this return wire its only job is to tell them that the fence is working good at the end. Until, of course, it's not working well at the end, and then they come back and say,
of course, and then they,
why didn't we do that?
Oh, boy. Why are there 3 terminals on your electric fence controllers? There's an earth terminal and there's 2 other terminals. Why?
Sure. There's two possible ways of using that center terminal. The first is to use it as a lower power output. So, for example, if I owned a farm and I had my farmhouse and I had some paddocks and fences that were close to the farmhouse, I might consider running those particular fences off the lower power. So instead of 8 to 9 kV, they'd be getting 4.5 kV on those wires, and that's because if my niece or nephew visits, they're not going to get the full zap of the high voltage. I'm being kind.
Got it. Right. So that's all it is. It's just a divider on the output. It's a tap on the transformer, is it?
We do it. We were the first to do it as a center tap on the output transformer because that actually gives us a second thing we can do with those 3 terminals. And I didn't invent this. I think a guy called Andrew McKean, an Australian engineer with another company, old electric fence company in Australia, invented this, and it's a system called Bipolar. So the center tap, the center terminal, if you like, goes to ground, and then you've got a balanced plus or minus output from the other 2. So you can have sets of balanced positive and negative wires on your electric fence. And now the attraction of doing that is that with a normal electric fence, let's call it conventional, you've got your earth in the ground, so the electric fence energizer at one terminal is earthed in the ground. You've got your live wires on the fence. Something walking up to that fence, a cow touches the fence, it's getting a shock from the live wire through its feet, and it's an earth return. A slightly more sophisticated method, and one that we employ in the game fences and security fences, is to have earthed wires on the fence, and they're wired all the way back to the energizer. So now if somebody's pressing through that fence, they're going to get a shock from the live wire and an earthed wire. So that's the best way of doing a conventional electric fence, and a lot of Australian farmers are doing it that way now. Their live wires can give a shock to ground, but they can also give a shock to the non-live wires in the fence. And Australian farmers use a lot of metal in the fence, so farm fences vary drastically around the world and even regionally in Australia. Australian farmers use a thing called a star picket. In America, that would be a T-post, and that's the intermediate post on the fence. And that's good for us for electric fencing, because it means any wire touching that steel post can be used as an extension of the earth. So those wires can be wired all the way back to the fence earth.
Oh, of course. Yeah, that would give you a much better earthing system, wouldn't it?
Yep, distributed. But with bipolar, you're really there are situations where it's hard for the animal. It's hard for the animal to get a shock with respect to its feet on the ground, and there's two reasons for that. You can have dry sandy soil, so you've got a hoofed animal on dry sandy soil and it's not well earthed. So you might have 5,000-6,000 volts on that live wire, but it's not going to deliver much of a shock if the animal is not well earthed. The other situation is this was brought to my attention by a gentleman in Canada who said that when they're grazing cattle in the winter on icy ground, you've got the same problem. Icy ground is not conductive, and that's kind of counterintuitive, isn't it?
It is. How so?
Well, all of the ions are bound in what is essentially a solid ice, and they're not available to flow.
Right.
So it's
okay. Yeah, I've never thought about that. Wow. Wow, that's fascinating.
Yeah, so bipolar gets around this by having these multiple live wires on the electric fence, and they don't do a lot when they give you a little bit of a shock if you touch either live wire, but if the animal persists and tries to go through the fence, it'll strike two live wires.
They'll touch both, right?
Yep.
Because in theory, if you're trying to stop people from getting in and you've only got an earth-based system, if they're not touching earth, they're not going to get the zap. So they can, go in with their huge 1-inch thick rubber sole sneakers, couldn't they? And not, in theory, and not get zapped.
They could. This area of security electric fencing is an arms race in that we initially, of course, electric fences were put up. They were big and scary. People didn't touch them. And then after a while, criminals started to work out that they could spread the wires, that half the wires were earthed, so that they could cut the earth wires, reveal a big enough space to crawl through. And there's all sorts of countermeasures that we've now been working into the system. For example, we can detect when they've cut the earth wires.
Oh, okay. That's interesting. How do you do that? Or is that secret squirrel stuff?
No, we're just running continuity on the earth wires.
Oh, okay. Right.
Yep.
Okay.
We can also put sensors on the fence that detect a change in tension on the wires. So if people are attempting to spread the wires to create a space, we can detect the change in tension on those wires.
Oh, how do you do that?
There's mechanical ways of doing it. So you simply rig up.
Of course.
You rig up a ferrule, if you like, that is bonded to the wire, and as they put tension on the wire, it pulls that and shorts it to something. So that's the older method, but we're actually using load cell type technology.
Right. So it's a strain gauge thing, and
Yep. Over tension, and away it goes.
Because the reason I was a bit shocked there is because I couldn't immediately off the top of my head figure out how you do that electrically. So it's about installing stuff on the wires and measuring tension and
countermeasures. As I said, in a lot of countries there are very rich people living close to very poor people, and the differential can be, for example, in Johannesburg, you can have, the average Joe has his house in the suburbs like I have here, but he has an electric fence around it because the break-in situation is just so bad that they're stopping them at the fence with an electric fence. It sounds terrible, and it's something unconscionable. We wouldn't consider doing it here in Australia, But
Of course.
in South Africa, it's something they've grown up with over the last 10 or 20 years. That's been one of the classic things that they use, like we use bars on our windows, in places here in Australia where break-ins are prevalent. People will put bars and security grills on the windows. In South Africa, they put up a security electric fence. And it's not only South Africa, South America, parts of China even. As I said, big market. A little bit sad in a way that there's people that are that desperate that they're trying to steal from the neighbours. But you can understand people attempting to stop that.
Of course. Yeah. So you guys, how many units would you be manufacturing and selling a year? How big is the electric fence market, and what market share do you guys have? I mean, you're one of the biggest. Have you got any numbers for that?
Interestingly, we're one of the biggest in some countries around the world and in some key markets. We've actually only got a little percentage of our home market in Australia, which is a bit frustrating.
Oh, really? That is unusual. Yeah. Why?
Well, we're a born exporter because of the nature of the product that we made. We were immediately tempted to export, and we did. Then, opportunity kept arising outside of Australia, and it's only more recently that we've started to focus on the Australian market. But the Australian market for electric fence energizers is tens of thousands of units per annum, but mainly in the agri space. So it's a niche market. Those in the business of electronics will realise that doesn't hit the millions that's required.
No, that's right. Thousands, tens of thousands is a decent niche market.
Correct. And so because we're selling all around the world, we're making about 10 to 20,000 units per annum out of our factory in Narangba, and we also arrange for some product to be made in other factories and shipped direct to customers. So we're closing in. We've passed our 400,000th product in the life of the company, and we'll close in on 500,000 sometime in the next 12 months.
Very nice. Now, one of the things I sort of gushed over in my video was that you guys have repair guides for these things. I was stunned. Like, it's so it's virtually non-existent to get repair guides of stuff these days. Why do you offer these very comprehensive repair guides with comprehensive troubleshooting and all sorts of stuff?
Well, being a relatively small company and having customers all around the world, we have to give a lot of long distance tech support. So having a good paper repair guide, and of course it's on the web these days.
Of course, it would pay dividends.
It does pay dividends. Our distributors like to repair the stuff themselves. They don't want to try and send it back because it costs a lot of money.
Okay. Right. Yeah.
And so long as they've got a tech who can read a multimeter, you might have realised the repair guides were quite low level. So they were.
Oh yes, absolutely. Yep.
We aim them at people who are not engineers, sometimes not even technicians, but are able to use a multimeter. And we insist, we actually test them before we authorise a tech repair, that they can use a multimeter, they can do a diode test, they can do continuity, they can look for a short circuit, they can measure voltages of various sorts. And by a step-by-step process, it turns out that you can solve and repair about 80% or so of the faults in an electric fence energizer if you use those simple techniques. Because as I said before, there's some components that are certainly overrepresented in the failure modes.
Right, yeah. Well, I'm looking at one of the repair guys now, and he is like step 9, check or replace Q4, like check or replace this MOSFET, because you've gotten to that point where, it's most likely that's the thing that's failed.
Yep, so if you...
Fantastic.
Again, divide and conquer is a great way of repairing things, isn't it? So if you start with the most obvious and work through, and each one of those steps is attempting to divide down where the fault might be, and then we have a table at the end, which is the faults that we've isolated by that method, and it might be only 10 or 11 of the possible, plethora of different faults an electric fence energizer might have, but they're the top percentage-wise of the faults that those things can have, and thereby if we give people the tools to do those simple checks, they can find and repair the energizers. And it's just remarkable how good these guys get. I've been taught over the years not to judge by somebody's schooling or
Of course.
because I've seen a guy who was a storeman in Texas become a good repair technician for electric fence energizers.
Absolutely.
He taught himself, and it was
Yeah.
now he does it, and he's very fast.
That's fantastic. and you sell even spare parts on eBay. You sell spare pulse capacitors and spare transformers, and so people really want to repair themselves if they've got a lightning strike and it takes out the transformer.
Individuals shouldn't repair them themselves because they could hurt themselves.
Right.
Worse still, if they're working on a mains powered energizer, they could make the unit unsafe. But there are a number of qualified technicians around Australia, and we just found it easier because these tend to be very small sales for us. We're a wholesaler. We're geared for selling 1,000 energizers at a time. To sell an individual capacitor to Joe Bloggs to repair an energizer costs us more in admin than we're ever going to make in that sale. So putting them up on eBay was just a brilliant move, and it's just saved us a lot of time. And there'll be 1 or 2 sales a month of these spare parts, and the guys have told me, the repairers have told me that they appreciate just being able to jump on and order it when they need it.
Oh, absolutely. That's fantastic. I was absolutely amazed about the repair guides and that you had an eBay store selling parts. I just couldn't believe it. I was gobsmacked. But of course, that's what this sort of niche industry sort of not demands, but sort of really, you sort of work your way into the point where, okay, that makes sense.
Well, it does, because because it's a niche and because we've got so many custom parts, you can't just go to a Farnell Element 14 and buy an output transformer or a pulse capacitor.
No, that's right. So you've got to offer them, and wow, just whack it on eBay. Absolutely fantastic.
Thank you.
Well, our hour's almost up, but I'm going to one last thing is that more towards your expertise is the microcontroller side of things. The original prototype that I found in the dumpster, it had a PIC micro. Why did you choose PIC back in the day? I think I know the answer. And what are you using these days?
Very good question. We were one of the first to put a microcontroller into an electric fence energizer. Putting a micro back in the day, back in the mid to late 90s, putting a micro within a few centimetres of a pulse discharge capacitor, had the obvious consequence. Some large manufacturers who I won't name actually went to market with units that were so unstable they would just regularly reset themselves. One of them even had a reset counter.
Oh, really? It's got an internal reset counter in like E squared prom or something?
It was actually displayable, so that I guess because the engineers wanted to know what actually happened when it went to the field, and any sort of arc on the fence would cause it to reset itself each pulse. Not funny when you're the engineer trying to make a product.
No, of course.
So we lined up a few different brands at the time. I'd been using Motorola since I left university. So, as I mentioned before, the venerable old 6.8 series, and we tried to, but we could not get them stable. We decided our test was that we would take a couple of wires from the output of the energizer, create an arc, and we had to make that arc above the microcontroller on the circuit board, and not have it reset. So that was the proof. The proof test was if it's stable, it's not gonna reset with an arc that close to it, because that can happen.
Yeah, but is this but that's going to be layout dependent and decoupling dependent and stuff like that. So how do you?
We had to start with a micro that was stable enough as well. But yes, then it's the layout. And I was lucky enough to have come out of audio. When I was a kid, I played with electronics, and my first love was audio amplifiers, guitar amplifiers, that sort of thing. And if you don't get the layout right, you get nothing but hum. So I learned about star earthing and
star grounding.
Yep. So look, applying those sort of principles to the circuit board for electric fence energizer is pretty important. You need to know what you're doing with your earthing, where your earth nets are, and what they do. Otherwise, you can end up with part of the discharge pulse on your 5-volt rail, and then you've got no chance.
I'm surprised to hear an electric fence guy
Mm-hmm.
use the term earth in
Mm-hmm.
regards to circuit ground.
Oh, yes.
Is that just a habit?
Mm.
Do you call in electric fences? Do you call the earth, or do you call it ground? So the terms are interchangeable.
We feel they're interchangeable, and that's just one of the few terms like that in electric fencing. The other one is, ground rod. Is it a ground rod, an earth spike? What is it? There's six different ways of talking about the same thing.
Yeah,
Mm.
right. So you chose a pick. The pick was what was just the best in these tests.
It survived. It was low cost at the time. We were using the
Yep.
one-time program board. So, I can't even remember the
Yeah,
numbers going back then.
that would be the PIC 16Cs. That because they
Correct,
Flash
yeah.
hadn't come out then.
Yeah, 16C 77, 71 rings a bell. So tiny amounts of program space. We're trying to do everything within a couple
Oh
of
yeah,
K of program
1K,
space.
512, 1K was a lot. Yeah.
Yep. So assembly language, and then we found C. So high-tech C, some of the listeners might be.
Oh yeah, that was good. Yeah.
So yeah, when he made his first C compiler, I was one of his beta testers, and
Oh, okay. There you go. And he eventually sold that. That's an Australian company for those who don't know. And he eventually sold it to Microchip. They still sell it as the high tech C compiler, I think.
just phasing
Do
it
they?
out. They bought everything into their XC, compilers now. So the XC was basically the last of the high tech. And believe it or not, I think now for a lot of their newer devices, they're using the GCU
Right.
compiler
Yep.
skinned underneath their MPLab X. So
Got it.
we're still using microchip picks, but we're not only using microchip picks. We're using some other controllers as well. But
Yep.
we're a pretty good customer of microchips.
Got it. Because the market has moved towards everyone wants a smart, Internet of Things device these days. So I notice your latest one has Wi-Fi and phone app and all that because the farmers just want to see get alerted on their phone, right?
It's absolutely. Australian farmers are trying to do more with less resources, whereas you used to have, a farmer, a farm manager, some farm hands.
Right.
Now there's typically one guy trying to do everything, and if he can get up in the morning and check his electric fences on his phone over breakfast, he can go and do something else for the day. That's half an hour to an hour.
Yeah,
of
that's
time.
super valuable to them. Yeah.
That's time. So absolutely, we need that. So you'll be interested to find what Wi-Fi chip we're using in there. I'm sure you'll recognise it once you see it.
Excellent. I'm sure I will.
And at this stage, it is a coprocessor, so we that design still has a microchip PIC as the core, if you like,
As
the engine.
Right.
But the Wi-Fi is another module with its own program on it. And then we've got our cloud server. We've got two of them, in fact. We've got one for the agricultural version of the app, and we've got another for the security version. So we've got a paid subscription service that people can use for their security electric fences, and for that matter, lots of other security devices can tie into that. But it was built around security electric fencing.
That makes complete sense to separate your processors in something like this. You'll just want the controller that just does its job, nothing else. And as you say, it's not susceptible. It's more rugged and robust, not susceptible to resets and due to arc overs and things like that. And then you've got your fancy pantsy whiz bang Wi-Fi, and even if that goes down, the controller's still going to work.
Sure, and you'll even find that there's a third microprocessor on that circuit board.
Oh, what does that do? Is that a monitor?
It's a watchdog. Yep. So it's an
it's a watchdog,
intelligent watchdog.
Right.
So are you familiar with Class C code or self-checking code?
No, not really. That's not my forte.
Okay, so any electrical appliance where the safety of the appliance is determined or dependent on the safety of the software, you've got to write the software in a very precise manner. It has to be self-checking. One bit error in that code will be detected, and it'll shut the thing down.
Oh, okay, got it.
So yeah,
and you do that. That's software. It's not a special Obviously, you're just using a regular pick. It's not like it's a, it's a CRC check-in micro or something like that.
Yep. So we're using we offboarded that to another little pick, and so it does the job. It does the job of sanity checking the other device and making sure that it's not going to do anything stupid, like pulse at 5 times a second, which could be dangerous.
Right. Is that part of the regulation and standards and stuff?
It's a method that we employed to meet the clauses of the safety standard. Other people have done it in different ways.
Got it. So it's not strictly required.
No.
I'm curious. Do you guys have to meet like FCC requirements and other EMC requirements, even for something that generates these massive? Like I would have thought, wow, you might be exempt because it's generating, like basically on an antenna, it's generating these massive pulses.
Well, of course, it's our electric fence energizer that is tested, and yes, there are some specific clauses and specific tests that they use for the output pulse, but because the output pulse is so short, and most EMC testing is done over an average over a time frame, it's obviously, because we do pass, it's not impossible to pass, even with something that's generating such a hideously noisy output pulse. But problems start when people then apply it to an electric fence, and if the aforementioned electric fence has those knotted wires on it in a live wire and has little arcs on it, you've got all frequency transmitters, haven't you?
Of course. Little spark gap transmitters all the way along you. Yeah, with a giant antenna on it. I mean, that's just,
Oh, yeah.
That's insane.
It is. And
wow.
problems
But I guess
can
you're
occur.
out in the middle of a farm and it doesn't, it's not going to interfere with anyone really. Maybe your neighbor's AM radio is going to pick it up,
Well, it used to be a big problem with telephones in rural areas before they went away from copper lines. Ticking on rural telephone lines was a very common problem, and of course that started to be a real issue when they started to put things like fax machines and then modems for internet on those lines, and they were just dropping out every second.
Right? Yeah, of course. Got it.
But the telcos fixed that by putting in coax and then fiber, and then of course now everything's on 3 or 4G, so that's a problem of the past, thankfully.
Course.
The more later problems have been with digital television. So occasionally we get somebody ring up saying, I've got to do something because my electric fence is resetting my neighbour's digital television picture.
Exactly. Because you'll see that during a storm, like your TV will just glitch and it'll freeze frame because it has to error correct because it's just been swamped by the magnetic field of the... Yeah.
Lost a few packets.
It's a lightning strike. Wow. Yeah. Oh, terrific. Well, thank you very much, Paul. This has been absolutely fascinating. Look at a niche market most people wouldn't have thought about. And you're one of the leading players in it. It's and it's all done here in Australia, which is, well, mostly.
Yeah.
Which is absolutely fantastic.
Our engineering group and most of the manufacturing is here.
Fantastic. So where can people check you out? Are you on social media? Can they follow you? Do you tweet? Maybe not.
Personally, I don't. The company, our brand, if you like. So Pacton's the OEM manufacturer and designer. The brand that most people see our own products under is a brand called JVA, short for joules, volts, and amps.
Nice. Okay. Yep. I take my hat off to that.
There's Facebook and other social media. You can tell I'm not a huge user of social media because I can't even name all of them off the top of my head.
Right, not a problem. I'll find what you do have and I'll link them in down below so that people can check them out. And hopefully I'll get a teardown of this new unit as well in due course.
Have fun with that.
So, yeah. Excellent. Will do. Thank you very much. And this one works, whereas the old one I found in the dumpster didn't work, unfortunately. So, yeah. So I'll be able to generate some spark gaps and stuff like that.
Do that.
Have some fun.
Yep. Have some fun with creating some...
Even though it scares the crap out of me, because anything over... I always say anything over 12 volts DC scares the crap out of me. I just don't want to...
Oh, that's called a healthy respect.
Yeah. It is. All right. Well, thank you very much, Paul.
You're welcome. It's been good.
All right. Catch you next time.
Okay. Bye.